Section 1.2, Scattergrams. We're going to begin with something called the Cartesian or rectangular coordinate system. This is just two number lines laid one on top of each other so the zero intersects. The horizontal one we refer to as the x-axis, and it has its positive side to the right and its negative side to the left. Again, the zero right here at the intersection. The vertical one we refer to as the y-axis, though this can change in different applications. We'll use different variables, but in general we kind of think of the horizontal as the x-axis and the vertical as the y-axis. For the y-axis, the upward direction is positive and the downward direction is negative. I mentioned that the zeros are overlapping right here. We call that point the origin, and it's one where we have the ordered pair 0, 0. And I'm referring to that as an ordered pair, so let's hit that definition too. An ordered pair is an x value together with a y value, and even though there's two values, an x and a y, it's still a single point when we plot it. And plotting is our main goal with these ordered pairs for now. So if we're going to plot a point, that would be the same as if they asked us to graph it. And the way we're going to do that is move x units on the horizontal axis and then move y units in the vertical direction. And notice that we're moving x units on the horizontal axis, but the y units are not on the vertical axis. They're in the vertical direction, and that's because after we've moved horizontally, we will no longer be on the vertical axis. So let me go ahead and show you how plotting points works with a few examples here. So we're going to plot each of these on this Cartesian coordinate system, and this time we've got a grid laid over to help us do the counting. And one of the first things that you have to do when you have a system like this and you're going to plot is you need to think about what scale. And the standard thought would be, let's go 1, 2, 3, 4, 5 type of numbering, but you just got to make sure that that's going to fit with all your numbers. So we have 1, 2, 3, 4, 5, 6, 7 squares in every direction from the origin. So we just want to make sure we don't have any numbers bigger than 7. It looks like the biggest number we have here is maybe a 5 or the negative 5. The 7/3 is actually 2 1/3, so that's smaller. So all these would fit on a scale of 1, so we're going to go ahead and use that. And I'm just going to put some tick marks on here, and then number 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5, 1, 2, 3, 4. Remember the left is negative direction, so this would be negative 5, and down is also negative. 1, 2, 3, 4, 5. Alright, so we've set up our scale, and now we just want to plot points. So the first one is 3, 5. So the x is 3, so over 3 on the x-axis, and the y value is 5, so from there go up 5. 1, 2, 3, 4, 5. So again, notice we're only plotting one point. We're not plotting a point at 3 and another one at 5, but over 3 and up 5, and that would be point A. Okay, so that's the idea, and we're just going to do that a few more times. So negative 2, 4, start with your pen or pencil at the origin, move left 2 because it's negative, and then up 4. And there's point B. And then 5, negative 3, over to 5, down 1, 2, 3. That's point C. And D is negative 1, negative 3, so left 1, down 1, 2, 3. And that's plotting ordered pairs. Alright, and then these have some zeros in them, so what's different about that is just we only get movement in one direction. So for E, we start at the origin, go over 1, 2, 3, 4, and then up 0. So we just stay right there, and there's E. On this one, we start at the origin, we go over 0, so we don't move, and then down 1. So there's point F. So with those zeros, you always end up either on the x-axis or the y-axis, and it's good to label those two. So let's go ahead and throw those labels in there. And you just have to be careful that you do it in the right order. Sometimes people, the 0, negative 1, will end up over here. You just have to remember that first move is over 0, so you stay put and then down 1. Alright, then looking at the final point, negative 5, 7/3. A couple ways to do this. One of them is you could think of this as a mixed number. So negative 5, 3 goes into 7 twice with 1 left over, so 2 1/3. Another way to do it would be to just go to the calculator and do 7 divided by 3. and get a decimal 2.33. Either way, just want to have an idea of roughly where that is. So left 5 from the origin, 1, 2, 3, 4, 5, and up 2 1/3, so up 2 and about 1/3 of the way to 3. You don't have to measure that super precisely, but just think a little bit closer to 2 than to 3, and then that's good enough for plotting purposes. And then that should have been letter G, and it is, so go ahead and label that. And that's how we plot ordered pairs. Alright, here's a quick follow-up to the plotting of ordered pairs that we did on our coordinate system. When you have the x-axis and the y-axis put together like this, you're forming 4 quadrants. Quadrant 1, Quadrant 2, Quadrant 3, and Quadrant 4. So they're always numbered like that, from upper left being 1, and then counterclockwise 2, 3, 4, and usually done with Roman numerals as well. And what they want us to think about here is what are the signs of the coordinates in each of those quadrants. So if you're in quadrant 1, then you have moved right and up. And right is a positive direction and up is a positive direction. So when you're in quadrant 1, it should always be the case that both your x and y coordinates are positive. If you're in quadrant 2, you've moved left, which means your first coordinate is negative, and then you go up, which means the second one is positive. So every point in quadrant 2 should have a negative first coordinate and a positive second coordinate. If you're in quadrant 3, you've gone left and down, so both of your coordinates will be negative. Left is negative, down is negative. And in quadrant 4, it's right, which is positive, and then down, which is negative. So everything in quadrant 4 would have a positive first coordinate and a negative second coordinate. Now when we do applications, most of our values for real life stuff are going to be positive, so we'll spend a lot of time in quadrant 1 where both the x and the y coordinate are positive, but we do get into those other quadrants now and again because negatives do have real life applications. Alright, when we're working with ordered pairs, we often want to think of there as being an independent and a dependent variable. So assume that a situation can be described by using the variables t and p, and assume that the value of p depends on the value of t. Then we call t the independent variable and p the dependent variable. And in terms of the ordered pair structure, the key thing for us to understand is that the independent variable is always the input or the x coordinate, and the dependent one is always the output or the y coordinate. So when you're if you can think of what order the ordered pairs are written in, the first one will always be the independent and the second one is the dependent. But sorting that out in an application can still take a little bit of work, so let's look at a couple examples of that. Let's let n be the number of hours that a student studies for an exam, and let s be the student's score on the exam. Identify the independent and the dependent variable. So what you're trying to think about there is which depends on which. Does your score depend on how much you study, or does how much you study depend on the score? And there's arguments to be made both ways. If there's any difficulty in figuring out which is the independent, which is the dependent, often thinking about it chronologically can be helpful. So what happens first? You study first, and then you take your exam and get the score second. So I would argue that the normal order for this would be that you would study first, so the n is going to come first, and then you're going to take the exam and that score is going to come second. And as I said up above, it's always independent first and dependent second. So identify the independent variable. There's two things you could say. From an algebra point of view, we think of the variable as the letter maybe, so you might say n. In a statistics point of view, we'd like to think about what that represents, which is the hours of study. So I would say it's best to list both. The independent variable is the letter n, which represents the number of hours of study. And so then the dependent variable would do something very similar. It must be the other letter, so that would be s, which represents the score on the exam. Alright, so let's have another look at that. Alright, let's go ahead and take a look at another one of those. Let's let P be the percentage of adults at age A years who say they are more stressed today than 6 months ago. What does the ordered pair 2164 mean in this situation? So what that ordered pair means really depends on which variable is the independent and which is the dependent. In other words, is the 21 the value of P or is 21 the value of A? So we want to think about that independent-dependent variable idea. What seems like the more likely prediction to make? That someone would tell you the percentage of people who are more stressed and you would guess what their age is, or they would tell you their age and ask you to guess what percentage are more stressed than before? Seems to make more sense to me that they would use that age as the predictor. So I think that A is going to be the independent variable and that P is going to be the dependent variable. And then that tells me that the ordered pair 2164 must be 21 years old because that's the value of A, and 64% because that's the value of P, which is measured in percentage. And then that's not an interpretation, but putting the units on is very helpful for getting that interpretation, but now we just want to put it into a sentence. And there's two ways we can do it. One would be left to right. Among 21-year-olds, 64% say that they're more stressed now than they were 6 months ago. That would be completely fine. I often find with those percentage questions it's easier and smoother to say them in kind of reverse order. So I would go with 64% of 21-year-olds say they're more stressed today than 6 months ago. So let's just write that out. And then that is considered our interpretation. So you could technically, I guess, just start off right there. 64% of 21-year-olds say they're more stressed today than 6 months ago. But I feel like there's a lot of thought that needs to happen before that. First of all, thinking about which comes first, the age or the percentage, so that you know which is which. And then just writing that with the units on it so that you can kind of lock down that thought and then put it into a sentence. All right, so we're looking at ordered pairs and we're looking at plotting points, and that's also that we can start doing scattergrams or scatter plots. And a scattergram or scatter plot is just a graph where we have plotted all of the ordered pairs in a data set. And then typically if you're doing a scattergram or scatter plot, it's because you're working with a data set that has some meaning to you, and so that's where these interpretations would start kicking in as well. So we'll look at one of those on the next page. All right, let's take a look at an example of a scattergram. The average hourly monthly pay is shown in the table below for various years. Let P be the average hourly pay in dollars at T years since 1970. Okay, so back in 1970, the average hourly pay was $3.24. In 2010, it was $18.61. And they want us to start plotting this, but one of the things we have to be careful with here is it doesn't say T is the year, so this is not T. T is the number of years since 1970, and that's going to be a really common thing that they do in this course, so we have to get used to that. And when they do that, we should add another column, which would be the value of T, the number of years since 1970. Sometimes I like to think of this as if you knew someone was born in the year 1970, how old would they be in these years? So if you were born in 1970, then 1970 you're still 0 years old. But 1980 is 10 years later, so that person would be 10 years old then. 1990 is another 10 years gone by, but since 1970 that has been 20 years, another 10 years, so now it's 30, and another 10 years, so now it's 40. So what's really going on there is subtraction. Let me bring in the calculator and just show you that. So if you take any of those years, like the 2000, and you subtract the 1970 starting point, that gives you that value that we ended up with of 30. So it's all just subtraction on these to get each one of those, though whatever the increment is here, it'll be the same there. So you can use kind of both of those patterns. That last one is 10 years later, so it should go up 10, but it's also subtraction. 2010 minus the starting year of 1970 is 40. So two ways to look at it, but definitely something that we want to get used to. And then the other thing is this column, and I think it's good just to throw our variable name on there for that one too, which is P. And typically in these problems, you're going to have your ordered pairs be input, output, or independent, dependent, horizontal, vertical. They'll be kind of laid out in the same level as the table. They don't have to be, but it does make sense to me that T would be the predictor and the price or the pay would be the thing we're trying to predict. All right, so let's try and create a scattergram for that data. And the key thing to do that is to set up a coordinate system so that all those points will fit and they'll be spread out fairly well. So first of all, notice all of our inputs are positive, all of our outputs are positive. So instead of drawing the horizontal and vertical axes through the middle of this grid, I'm going to draw them right on the edges of the grid. And that's really common with our application problems because we're typically working with all positive values. So then we're making quadrant 1 our point of emphasis, and we're using all of our space for quadrant 1. The next thing to think about is how to number. So for this one, let's label which is which. This is the horizontal, so this is going to be our first one, T, and the vertical is going to be the output or dependent variable, P. And we just want to think like, what's a good scale? Standard scale is 1, 2, 3, 4, 5 type of numbering, but we're never going to make it to 40 if we do that. We could just do some trial and error. What if we went in 5s, 5, 10, 15, 20, 25, 30, 35, 40? That's not too bad. We might even end up going with that. So here's a way that we can make scale decisions that's a little bit more mathematical. What you can do is take the grid and count how many squares you have. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 squares in the horizontal direction. And then take the biggest number you need to plot, which is that 40, and divide it by the number of squares you have, which is 14, and then round that up to something nice. If you just left it right at 2.857, then if every square was 2.857, you'd start at 0, end at 40, but that would be a horrible scale to use, very confusing and messy. So round that up to something nice, 3, 4, or 5, I would say. You never want to go more than double because the more you round this up, the more our graph gets squeezed in this way. And so if we go more than double, we'll be using less than half the space. So I think normally I would round that up to probably 3 or 4. But because all of my values are multiples of 10, it'd be nice if we went with 5 instead, because then these are all divisible by 5 and they'd all end up on grid lines. So I'm going to do that. So 5, 10, 15, 20. 25, 30, 35, 40, 45, 50, 55, 60. So just a quick thing to point out, my scale is what each square is worth. So even though my numbering went 20, 40, 60, you want to think about if you were counting each square, and that's 5, 10, 15, 20, so our scale there is 5. All right, now we're going to switch to the vertical and think about how to number those. Now here it's not really going to be a factor about making sure that these are divisible by our scale. These numbers are messy, so that's not going to happen. So we just want to think about making sure that 18.61 fits on this number line and that it's fairly high up. So I'm just going to use that same trick of taking the biggest number and dividing by the number of squares, but I don't think that's 14 in the vertical direction, so let me count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So take that 1861, divide it by 11. That says if we started with 0 and went 1.69 all the way up, the top would be $18.61, but that's messy, so I'm going to go in 2s. So 2, 4, 6, 8, 10, 12, 14, 16, 18, and then we have 20 and 22 as well. Alright, so that is usually the most work of doing one of these plots, is to label your axes. And speaking of labeling, it's probably good to say here that this is years since 1970. And then on the other one say that this is the average pay, or maybe at least just throw the $sign on there to remind us. And then start plotting ordered pairs. So I'm not going to write this for all of them, but this first line, it's 0, 3.24, and I'm just going to think of it that way for all the first. Input, output, horizontal, vertical. So over 0, up 3.24, so this is 2 and 4, so 3.24 is a little bit more than halfway between 2 and 4. And then just keep going with that. Over to 10, and up to 7.15, this is 8, this is 6, so 7.15, maybe around there. Over to 20, up to 10.78. So a little less than halfway between 10 and 12. Over to 30 and up to 14.32, so just a little bit above the 14 mark. and then over to 40 and up to 18.61, so a little bit above the 18 mark. You're not going to get these perfect, not with values like 18.61, but you want to do a decent job of getting them in roughly the right spot. All right, so there's a scatter plot, scattergram. Let's go ahead and look at what their follow-ups are. Did the average hourly manufacturing pay increase, decrease, stay approximately constant, or none of these? So basically what they're wanting us to look for there, is it going up, is it going down, is it horizontal, or is it chaotic? And I'd say fairly clearly this is going up. So because it's going up, we would say the pay is increasing. Which is good. You'd like to see the average pay for people increasing over time, right? And then another follow-up, did the 10-year increase in the average hourly manufacturing pay increase, decrease, stay approximately constant, or none of these? Now when you first hear that, you might think it's just the same question, but they're not asking quite the same thing. Here it was just, was the pay going up or down? Here it says the rate at which it's going up or down. So if you look at this, it looks like it's a fairly constant climb as we go in this direction. And if that's the case, that it's fairly constant, then we would say it's a constant rate of change for the pay. And one of the key things that we want to learn, constant, one of the main things that we want to learn is that if you have a constant rate of change, we get kind of a linear pattern, and we'll be studying these linear patterns at first. But then there's other things that can happen where the rate can be increasing, and if you had an increase in the rate of change, you would see a bend like that where it's going up, but it's going up faster and faster. If it was a decrease, then it'd still be going up, but the steepness would be leveling off. So that would be an example of what a decrease looks like. There's an example of an increase. The constant should look linear, and then this would just be kind of chaotic. All right, so final note here is about what we were doing with scale. To decide on a good scale, divide the largest number that you're going to plot by the number of squares in that direction. And that's usually going to be a messy number, so round up a little bit. Less than double would be kind of the rule to go by, to something that's a nice number. And if you do that, that'll give you a scale that is the value that each square would be worth, that if you do that, you should get a decent number in. So again, just a reminder of how that worked. The biggest number we needed to plot in the horizontal direction was 40, and I counted the squares, there were 14, so 40 over 14 was 2.85. I rounded that up to 5, which was a nice number that was less than double. And then in the vertical, we needed to plot 18.61. That was our largest number. When we counted the squares, there were 11. And then I got this when I divided, but that's messy to use as a scale, so I rounded that up a little to 2, which is much nicer. All right, that wraps up section 1.2.